This is Shelley Physics Introduction to Kirchoffs Rules edition, brought to you by the Washington Nationals. Unofficially, not really, but they just won that World Series so big that they're going to be champions, national champions, world champions for 2 years in a row. I'm just thinking about it, and that's just with only one World Series win. Let's see if that happens. Anyhow, today we're going to be looking into what's called the complex circuit. Now, if you look at the circuit, it may look like a combination circuit, but there's one little factor that's getting in the way here. We've got this other EMF source, it's 10 volts. Now I'm backing away from internal resistance in batteries here. Of course, each of these batteries would have a little bit of resistance or maybe a significant amount. And you could just as easily add that onto the resistance that's on that branch. But we're just going with the EMF for now. I'm going to label these. There's an EMF here and an EMF here. But this is called a complex circuit. You can't categorize it as series, parallel, or combination because of that EMF source in two different branches of this circuit. So how do we go ahead and solve this? And that's what Kirchoffs rules help us with. Now, Kirchoffs rules, they're not laws because they're both based off of laws. They're conservation laws. Kirchoff has two rules. One is called the loop rule, and the other one is the junction rule. The junction rule states that the sum of the currents at a junction, I'm going to say jumped, that's a jumped, junction, there we go, J-U-N-C. I had a spelling little snafu there. Okay, knew that looked a little weird. Sum of the currents at a junction equals 0. Probably doesn't look very helpful, but in fact it really is. This is called the junction rule. Perhaps I should have spelled it out first. It would have been more apparent when I'm labeling. And really, it's coming from the law of conservation of matter, or more specifically, charge. The fact that the number of electrons that come into a junction equal the number of electrons that leave that junction. So it is from a conservation law. And Kirchoff's other rule we'll be looking at is the loop rule. And this is our other major conservation law. Can you guess it? I'll get to that in a second. What it states that if we sum up the potentials in a loop of a circuit, guess what? That'll equal 0. That sum will equal 0. Again, it may not look very useful, but it is, and you're going to see how it is. But what this is saying is if we take a loop, take any loop, like say if I start at one point in the circuit, take any loop or route back to that same point, the sum of the potentials along that loop are equal to 0. Some of those potentials will take away energy, potential energy, some will increase that potential energy in the circuit. But if we go from one point to another, the total work done is 0. So the change of potential is 0. Therefore, the sum of all the potentials is 0. So we will have potentials we're adding and summing that are going to equal to 0. And if you didn't catch that drift, this is from the law of conservation of energy. Okay, looks like I need another of here. There we go. Law of conservation of energy. So these are the two rules. They're based off of conservation laws. And if we apply them, then we can solve this complex circuit. So here's the circuit laid out. We have 4 volts down here, 5 ohms, and so on. We've got the 10 volts, 2 ohms, and 8 ohms. I'm going to come back to this so we can see a little bit more dynamic result. And thank you to fet.colorado.edu for supplying these wonderful simulations for teachers all around the world. So thank you, Fet. All right, so we're going to come back to that. We're going to check out some voltages. I just moved the whole frame there. Some voltages, some potentials, and mainly the currents. What is the current through each section of this circuit? That is what we're really going to be looking for here. So what can we glean? We know the EMF provided by each source, We know the resistance of each resistor. So the first thing we're going to do here, I like to make lists for people to follow, list of directions, and sometimes that gives you a starting point. Occasionally when you approach a problem, like, oh, where do I start? Where do I start? But if you can identify it as, oh, this is this type of problem, you go back to a problem-solving method, and I think that's what will really help you at least get started. Once you practice that, it gets a lot easier after that. So first thing, establish a direction of current flow for each branch of the circuit. Apologize for my old school like defining. What that does is gives you time to write it down. If you are taking some notes on this, I really hope you do. But it helps you think about it. As you're writing, you're thinking about what's being stated. So establish a direction of current flow for each branch of the circuit. It doesn't have to be the right direction. We're going to see in the end, if you end up getting a negative value for the current, then you just guess the incorrect direction, and the negative corrects you. And you actually have the result. You have the direction of the current and the value of the current in the end. Number two, we're going to apply the loop rule. For each unique. I needed a unique word there. And the word is unique. Unique loop of the circuit so that all elements are represented. I use the word elements there, meaning batteries or resistors, EMF sources. Later on, we're going to include capacitors. Not later on in this video, but later on in a later notes video. Okay, and third, apply a junction rule. To account for every unique current. I. Okay, so we're going to be doing some labeling here so we know what I values we're looking for, what currents we're looking for, and what I mean by unique loops. So you're going to be able to see this in a moment here. So I'm going to come back to this list, problem solving list there. All right, so I have a circuit here. The first thing I'm going to do is establish the direction of current flow for each branch of the circuit. So what do I think? Well, my guesses would be this. You see, batteries, they apply a current, tend to apply a current from negative to positive, and the stronger the batteries win. So the batteries with a greater EMF are going to push more. So this is 10 volts. So I'm going to imagine that there's a current flow this way. Now, where the current's going to be important is across the resistors. So if I have a current flow in this direction across the 10 volt EMF, then there's going to be a flow going in this direction. I started to label the resistors, R1, R2. Looks like I left one out. So I'm going to label this one R3. All right, so along with R3, I'm going to label the current I3, current 3. So that current is going to be in this branch of the circuit. Now, if I did have another resistor down here, I3 would be passing through that resistor as well. So that's just something to take a note of. So I3 passes through 10 volts and through this 8 ohm resistor. And I'm defining the direction as this kind of possibly at this point, a counterclockwise kind of flow. So my guess also down here for this battery, I don't know, negative to positive, I'm guessing that the flow might be this way. So I'm going to define a current is flowing downward and call that I1. All right, so I1 is going to travel this way, or flow that in that direction, I'm guessing. Now what about this over here? I might have a current coming up. Is it, this flow agrees with I3, so is it going to be cyclical like this? So through the middle, is it going to go up or down? I'm just going to be a little silly here. I have a guess that it's going to go down, but just for argument's sake, just so you can see the result in the end, I'm going to just randomly define up as the supposed direction of flow, I3. Sorry, that would be I2, current 2 to go along with resistor 2. So it's sort of like when you draw a force diagram and you pick a right as positive. It's just an arbitrary choice. In the end, if you end up getting a negative acceleration in that case, then you know that your positive direction isn't really positive, that the negative direction, as you first defined it, is actually the direction of the acceleration. So likewise, if you select an incorrect current direction, it's going to turn out okay. You'll see it in the end. So that was our first step. I've got a current flow through this branch, and through this branch. So all resistors have a flow across them. That's number one, establish the direction of current flow for each branch of the circuit. Number two, I'm going to apply a loop rule for each unique loop of the circuit so that all elements are represented. It is possible to write out too many loop rules, and you might end up with a couple of equations that when you put them together and solve them as a system of equations, you might get some weird answer like 2 equals 2 or 0 equals 0. That means those equations are not unique. I'm sure there's a better mathematical comparison between those kind of equations. I'm a physics guy. I tend not to memorize all those wonderful mathematical names for things. So anyway, so we're going to look for some unique loops. As long as we have equations that incorporate all the elements, we're going to be good to go. But before we get started, look at our unknowns. How many of them are there? 1, 2, 3 unknowns. Besides that, we know the resistance values of everything else in the circuit, all the other elements, and we know the potential values, the EMFs for the batteries. So the only unknowns are I1, I2, and I3. So that's 3 unknowns, which means we need 3 equations to solve for those 3 unknowns, to solve for systems of equations. So we're going to start out with the loop rule. Sum of the potentials in a loop equals 0. All right, my first loop, I do like to start behind a battery. It gives me a positive number to start with, behind meaning on the negative side. So I'm going to start right here. And my first loop, I think I'm just going to go around the outside, okay, like a big track. So my first loop, we're going to start in this battery. We're going to go around this way, around like that, come around, back through there, and to the beginning again. So this is one loop around the outside. I'm going to start with potentials. If I go across a battery from negative to positive, that's going to be a positive potential change. If I go across a resistor, you've got to be careful. I'll have to look at the flow. Actually, let me back up a second here. The flow does matter across the resistor. If we go from this side of the resistor to this side of the resistor, and the flow is from top to bottom, if this is A and this is B, then we will have a negative change in potential, a negative IR. If we're going in this direction against our established direction of flow, according to how I defined the directions in number 1, okay, so this is my established current flow. If the flow is up and I'm going in the loop direction down, I'm going to add potential, because in that loop, as we go from A to B, there should be a drop in potential. But if I go from B to A, there should be an increase. It's like going down a hill compared to up a hill. Now if I start at the bottom of a hill and I force my way up it, I've increased the potential. So going against the established flow is like increasing that gravitational potential up a hill. So I'm going to start here. From negative to positive will be a positive change of 10 volts. All right. Now I'm going to move ahead to this resistor. the current flow hits this resistor. Now from here to here, I'm going in the correct direction of flow. My loop is in the same direction of flow. So there should be a drop in potential, a negative I1 R1, or resistance 1 is equal to 5 ohms. So I'll go ahead and plug in 5. Next, I'm going to go from the negative side of this 4 ohm electromotive force to the positive. So that's a positive change. Negative to positive is positive. So we're going to add 4 volts to that and come back around this way, again in the correct direction, the same direction as I3 has been established. So that's going to be a drop, or a negative change in potential across that resistor. That's I3 times R3. I3 is unknown and R3 is 8 ohms. And then I get back to my starting point again. So the sum of all this should equal 0. Okay. Now I can simplify this a bit. I'll put all my terms, like terms on one side. I got 10 plus 4 is 14. So in that loop there's a positive change in 14 volts. And if I add my i's to the other side, that'll be 5I1 plus 8I3. And do be careful and check your work when you do this quick algebra. I've made many mistakes before. Put a positive on one side instead of a negative. I'm just going to double check this now. Adding the 2 negatives to the other side should make them both positive. So there I have one equation relating I1 to I3, current 1 to current 3. Next I'm going to do a second loop, because I haven't made a loop equation that included this resistor 2. So because I'm not feeling very creative right now, I'm going to start in the same place, but do an inner loop here. Okay, I'm going to come back around to this point through these 2 resistors. So my second loop, I'm going to start at this point again. There's going to be a positive 10 here. And then, all right, now in this loop, I'm going to go against my established direction of current. So if this direction is correct, if I start here and go to this point, there should be a negative change going up, but my loop is taking me down across R2. So there's going to be a positive change. So, oops, I didn't mean to put an equal sign there. Well, 10 plus, I am summing all the potentials in this loop. So 10 plus I2 times R2 is 2 ohms. All right. And then I'm going to come around this way to finish my loop off. I'm going in the correct direction of my established flow, and I'll have a minus then. So I'm going to subtract potential. I3 times R3 is 8 ohms. All that equals 0. So again, I'm going to simplify. 10 equals, and just to keep the I2s and I3s in order, I'm going to have a negative 2I2 and add the I3 term to the other side, plus 8I3. There's my second equation. I need 3 because I have 3 unknowns. So you might think, well, can we do a third loop and not worry about the junction rule? No, because if we do combine these 2 equations, if you try it, go ahead and try to combine them. Maybe solve this one for I3 and plug it into I3 over here. I guarantee you're going to get the same exact equation by combining these 2 that you will from the loop rule around there. It's not unique. You've already accounted for all the elements in the circuit, so there's no other unique equations to create. Therefore, we need to always include a junction rule. And I'll flip it around here. Let's do the junction rule. All right. So the junction rule, sum of the currents at a junction equals 0. And we'll rewrite that. Okay. That is not a great junction. There we go. So there are 2 junctions, but there's only one unique junction. Only one of them is really unique. Actually, they're both the same. According to our established flow from this junction, I3 comes in right there. Zoom in on that point. I3 flows in. I2 also flows into that junction. And I1 flows out. So do you see, if these are electrons, or I should say, if these are positive holes flowing into this junction from the direction of resistor 3, flowing into the junction from the direction of resistor 2, then there has to be positive holes, positive charge, flowing out in the direction of I1. So the current flowing in equals the current flowing out. The charge in equals the charge out. This is the law of conservation of charge at work. Okay? Zoom back out. All right. So if I pick this junction, it's not at all different from this junction down here, because with 2 and 3 coming in and 1 going out, guess what's going to happen down here at this junction? 1 goes in and 2 and 3 go out. We're going to have the same equation if we use both of those. So I'm just going to use the one up top. I will use positive meaning in and negative meaning out. Zoom that up there. All right. So whenever I have a positive current, that means the flow is going in. So if I start looking at these, I've got I2 plus I3 flowing in to that junction. And I1 is current flowing out. So that means the charge is going to go away. So I'll use a negative for that. And that's it. That's the junction rule. Now if we looked at this junction rule, we would have I1, I'll put a big OR here, I1 flowing in, so I1 comes around here, current 1, flow this way, I1 goes in, and 2 and 3 will both flow out, so we would have a negative 2 minus I3 equals 0. Now if you look at those two algebraically, they are identical. If we add I1 to the other side and subtract 2 and 3 from the other side, we would get that same exact equation. So that's what I mean. These are not unique equations. I'm just going to use one of them. I'm going to use this one. I am going to, though, before I get started, or before I go to the next step, I'm going to reorder these so that one's in the front. So I have a negative I1 plus I2 plus I3 equals 0. Oops, that's kind of what I had. Oh, no, that's it. Just reordered them. And that is our third unique equation. So what's important about this is it says how those currents compare. We have a list of currents involving the potentials on this side, but we don't really know how they compare. This junction rule gives us that comparison. So I'm going to rewrite that third equation down here, negative I1 plus I2 plus I3 equals 0. And that's our body of equations. From here on, it is an Algebra 2 problem, okay, or depends on when you took it, I guess. So this becomes an algebraic problem, a system of equations. There are many, many ways to solve it. I think what I like doing is taking these and plugging their equivalents into here, because I've got an I1 and I3, I2 and I3. They both compare to I3. So from equation 1, what does I1 equal? It'd be 14 minus 8 I3 all divided by 5. And from equation 2, what does I2 equal? I2 would be 10 minus 8I3 divided by negative 2. All right, and then I'm just going to plug them into this expression, into equation 3. Negative I1. You know what? I meant to plug them in, so I'm just going to rewrite this again. Move it up a bit. So I'm going to plug this in here and plug 2 into there. So we've got 14 over 5. It's going to be a negative on the outside here. So So negative 14 over 5 minus 8/5 I3 plus 10 minus 8 I3. We do have a negative 2 over here, so go ahead and keep that the same to make it look like I'm doing the same thing here. Plus another I3 equals 0. So what I've done is I've just collapsed this down to one equation with one unknown. This is solving by substitution. Here we have 2 and 4/5, so that'd be a negative 2.8, distributing the negative there. And 8/5 is the same as 16/10, or 1.6. And we'll have a negative 5 here. I already started putting plus here, so you know what, I'm going to take this term. Negative 8 over 2 is positive 4 I3, and now I'll take a negative 5 there. 10 divided by negative 2 is negative 5, plus I3 equals 0. We're going to combine our I3 terms. 5.6 plus 1 more is 6.6 I3. And negative 2.8 minus 5 is negative 7.8. And we get a current 3. And I'm going to add that. So 7.8 divided by 6.6. Bring up my calculator here. This is off screen, but if you take 7.8 divided by 6.6, get a 1.18 repeating, so I'll just say 1.19 amperes. There's I3. Okay, you don't really need to follow along this if you're good with your algebra, but now I have equation 1 and 2 to solve for I1 and I2. I1 is 14 minus 8 I3, which I have established now. I've got a value for that, divided by 5. And current 2 is 10 minus 8 times 1.19 over negative 2. Okay. Let's solve those and get a result. 1.19 times 8 is 9.52. 14 minus that, divided by 5. 0.896. Looks like I'm using 3 sig figs, so I'll take that. So I1. And for I2, let's check that out. 10 minus that 9.5, what was that, 9.52? And divide that by 2, or negative 2. Alright, so we're actually getting a negative value here. 10 minus 9.52 is a positive number, divided by this negative number, is negative 0.24 amperes. And one thing you can do is you can add this to this, just in value. Our if we go back to this expression up here, we're going to see that I1 is equal to, if we bring the I1 over on this side, I1 is equal to 2 plus 3. So 2 plus 3, let's move that up there. 2 plus 3 is equal to 1. So that's how they all relate. But if you take a look, I've got a positive 1.19 amperes, positive 0.896, and negative 2.4. So this means I just I guessed the direction backward, or I guessed the backward direction. Okay, guess the backward direction. So putting that back onto the diagram here, my flow I got here for I1 is 0.896 amperes. Flow I got for I2 is negative 0.24, and I3 on this side was the 1.19. All right. So here's where I'm saying in the very beginning, when you establish your directions, if you end up with a negative value, that just means the flow is actually downward instead of upward. Not a big problem. Go ahead and check it, and if you ever work in these circuits or you just want to practice your own, I really encourage you to use FET, because you can set up any of these circuits that you want, read the current values, and get your results. So here I had the circuit set up. What I'm going to do right now is add an ammeter into the mix. There we get R3. Okay, we calculated 1.19 from some rounding. This comes up with 1.18. So that's the flow through this entire branch. Let's break this one now. And reconnect that in a funky kind of way. There's the 0.27. I had about 0.24. So we got a little bit of rounding going on here. And here's our last one. There's a 0.91. I came up with 0.896. So a little bit of algebraic rounding is the difference there. So that comes to the end of this first one. I'm going to take you through a couple more examples. If you look them up, go through Kirchoffs Rules, example 1 and 2. They're going to be just of increasing difficulty. Also, as you're going to see, 3 equations with 3 unknowns isn't too hard to solve algebraically, but occasionally you're going to have something like 5 different unknown currents, or even more. So I'm going to show you a method, and you probably will think back and remember this, but using matrices, you can stack up your equations and solve for your unknowns in a very quick way using your calculator, your graphing calculator. So that's coming up, new examples. I hope this is helpful in getting you started with Kirchoffs Rules.